Okay, so today we are going to do another important concept in logic known as rules of inference, which is used to simplify many things in propositional logic as well as in predicate logic. So let me talk about rules of inference. It's a very important concept. So first I will define few terms which are important, then I will give you an example. The first term is what is known as argument. What is an argument? So argument is a sequence of propositions. Okay, propositions. Of course, I am talking about in proposition logic actually. So a sequence of proposition is known as argument. So in the argument, all except the final, in this sequence basically all except the final. So all in the argument they are called as premises. These are premises. Okay, and the final proposition in the sequence is called conclusion. Fine. So I talked about argument. So argument is a sequence of propositions except final proposition, which is known as conclusion. All the previous ones are known as premises. Okay, and we say that an argument is valid if truth of all premises, truth of all its premises implies is that conclusion is true. Okay, so if all the premises are are true, then its conclusion is true. Okay, then we say that argument is valid. We also have another definition, an argument form. An argument form in proposition logic is a sequence of compound propositions, involving propositional variables in its premises. The conclusion is true if the premises are all true. Okay, so then so this is about argument form. Okay, And now I'm going to give you a example for this. Suppose P is a proposition. You have a current password. And Q is a proposition. You can log on to the network. You can log on to the network, right? So we are going to ask, is it, if we write down this, is it a valid argument? We may ask this question. P implies Q. Is it a valid argument? So we know that both P going to Q is true, okay, and P is true. Therefore, Q, the conclusion, is true, right? So this is a valid argument, right? So if P going to Q is true, P is true, then Q is true. So these are the, so this argument is valid. So note that we have P going to Q, meet P going to Q is a tautology. Okay. So this is in general true. Now, truth tables can be used to show that the argument in form is valid. But for larger systems, it is a bit tedious approach. It's a very lengthy approach. So another approach is rule of inferences. So now I'm going to talk about rule of inferences. So I'm going to in fact make a table for you. So what is this another approach? So first, establish the validity of some relatively simple argument forms. And these are called as rules of inference. Okay, and so this way, rather than making truth table, we can actually simplify the process. So here is a truth table for, I mean, here is a table on rule of inference. Rule of inference, tautology, and name. There are some specific names for these things. I'm also going to mention those names for you. First, P implies is Q, therefore Q. Right? If P is true, P implies Q is true, then Q has to be true, right? So the tautology is P meet P implies Q gives you Q. And this is known as modus. Its name is modus ponens. Next rule is negation of Q, negation of Q, P implies Q. So if negation of Q is true, P implies Q is true. Therefore, negation of P is true. So in other words, this is negation of Q, join P implies Q, give implies is negation of P. This is known as modus tollerness. Next, if P implies Q is true, Q implies R is true, right? Therefore, P implies R is true. So the tautology is P implies Q, meet Q implies R, implies is P implies R. Okay, and this is known as hypothetical syllogism. These are just names. Okay. Next, the important one. P join Q is true. Negation of P is true. Therefore, Q is true. Okay. So tautology is P join Q, negation of P times Q. Okay, so this is known as disjunction syllogism. Next, P is true. Therefore, P union Q. This is simple. P Q join Q, known as addition. Right. Similarly, P and P meet Q is true. Therefore, P is true. And tautology is this, and this is known as simplification. Then we have P is true, Q is true.
So,
Therefore, yes.
sir, in second column, the P joint Q, P meet Q, right? In second column.
You want to say addition?
Nah, simplification. P.
Oh,
Sir,
sorry.
P meet
Yeah,
Q.
yeah. Yes, it is meet. Correct. Correct. Yeah, so you see when you write so many, there will be errors anyway. So you can check that is good. Simplification. Then we have P is to meet Q is. Tautology is P. This is known as conjunction. And finally, the last one, P join Q, negation of P join R, therefore Q join R. So this is P join Q, negation of P join R times Q join R. This is resolution. Okay. So these are the basic rule of inferences. 1, 2, 3, 4, 5, 6, 7, 8. 8 of them are there. Now I will show you by an example how this can be used, in simplification. So let us look at an example. So we need to find the rule of inference in the following argument. Find rule of inference. Right. So argument is, it is below freezing now. Therefore, it is either below freezing or raining now. Right. So this is the statement. I have to find the rule of inference. So what we need to do, I will just make sure that what are the propositions. The P proposition is, it is below freezing, right? It is below freezing now. And Q is a position, it is raining now. Then what is the argument? Then argument is of the form P is true, therefore P join Q is true. This implies that the argument uses the addition rule. Okay. We have found the rule of inference. Okay. So similarly, you can find many others. So now I think I will give you an example where using rule of inferences, we can build the argument, the larger one. So let me give an example. Okay. Another example. So in this example, so we need to show that the hypothesis there are many statements, it is not sunny this afternoon. Okay. And it is colder than yesterday. Okay. Next, we will go swimming only if it is sunny. Okay. Then if we do not go swimming, if we do not go swimming, then we will take a canoe trip, and if we take a canoe trip, then we will be home by sunset. So we need to show that all these statements, I mean, this is our hypothesis, lead to the conclusion that we will be home by sunset. So how do we do this? So it's a little bit lengthy, but of course we can do it. So what I'm going to do now, I will write down, I first identify the propositions. So P is, it is sunny this afternoon. Right? Q is, it is colder than yesterday. R is, we will go to swimming. So we need to just identify the propositions. We'll go swimming. Okay. S is, we will take a canoe trip. And T is, we will be home by sunset. So there are 5 propositions that we identified out of these statements. Now our question is, so what is the hypothesis then? So we can write down using these notations. The hypothesis become is, you can see that negation of P meet Q, right? The first one. It is not sunny this afternoon and it is colder than yesterday, right? So this is this, combining these two. Then R going to P, negation of R implies is S, and finally S implies is T. So from these basic propositions, I can form the hypothesis like this. Now I need to give a valid argument with this hypothesis that the conclusion is T. Okay, so we need to give valid argument such that the conclusion is T, right? So I think let me start step by step. The first one.
Excuse me, sir.
Yes, please
Good
ask.
morning, sir.
Yeah, good morning.
Sir, can you explain how R implies P here?
Where is R? I have not written R. This is S. This
Not
is
here,
S.
sir. The second hypothesis.
R implies P, right?
Yes, sir. Shouldn't it be P implies R? Because I don't know exactly, sir. Can you explain it, please?
Yeah, okay. Let me go one by one again, because sometimes these 1 minute. Okay. Yeah, so the first one is what? It is not sunny this afternoon and it is colder than yesterday, right? So it is sunny this afternoon is P, right? So negation of P, it is not sunny, right? Meet Q, correct?
Yes, sir.
Okay. we will go to swimming only if it is sunny, right? So
Yes, sir.
R is we will go to swimming. I mean this, right? Only if this is true. P, right?
Okay, sir. Okay, but couldn't it be P implies R?
No, I think it's the way it is written in the English. That's why it looks confusing actually. Okay. So we will go to swimming only if it is sunny. Okay.
Okay, sir.
Then we have all these hypotheses. Let me actually do it one by one so it will be more clear. So let me write down the steps. Okay. So our actual problem starts now. Step and reason. So first is negation of P meet Q. So okay, this is our hypothesis, the first one. Okay. Second is negation of P. This is simplification using 1. So using this hypothesis, we use the simplification rule. Okay. So we arrive at here. Okay. Remember what is the rule? I'll just write it down in the first case, then maybe I will not write it down. Simplification rule is P meet Q, therefore P. Right. So this is the simplification rule if you remember. So here it is negation of P meet Q, therefore negation of P, right? Simplification. Then third is R going to P. This is again a hypothesis, the second hypothesis. Okay. Then what we do? We get basically negation of R. Now this time negation of R using modus tollens using second and 3. We use second and 3. This and this will give us this. Okay. Using this this rule. Okay. Next, fifth is negation of R implies is S. This is again next hypothesis. So that means again we get S using models of using 4 and 5. Okay, these two will give us this using this rule. Seventh is S implies T. This is the last hypothesis. Okay, then again using 6 and 7 we can get 8th, which is T. So rule is modus bonus using 6 and 7. Okay, so this is how we get the answer that T is the conclusion. Now if you make the truth tables, the truth table will have 32 rows 32 rows. So this is a much simpler way of doing it actually. Okay. So how to apply rule of inference in computing these things, right? So now actually I'm going to give you another very important thing known as resolution principle. Sorry. Resolution principle.
What is the TT32?
Hmm?
Yes.
Truth table. TT means truth table. I always write down short form. So actually the same problem can be solved using truth table, okay? Right, so if you do the truth table business, we will have 32 rows. So we are avoiding this. We are not doing this actually. I just mentioned this thing to you, okay?
Sir.
So we are using rule of inference, and that's why I'm showing you the rule of inference are useful things. So they simplify our calculations. So rather than making truth tables, we can apply the rule of inference. That's the only thing I want to give you the message. Okay. Now, in order to explain to you resolution principle, I need to again give you some definitions. First, literal. A variable or negation of a variable is called a literal. Okay. And a disjunction of literals is called a sum. Okay. Similarly, a conjunction of literals. So literal is a variable which is so basically literals are variable or a negation, maybe p or negation of p, something like that, is called a product. Okay. What is a clause? A clause is a disjunction of literals. It's a disjunction of literals, that is, it is a sum. Okay, that is a clause. Now there is now I can tell you what is resolvent of two clauses. Suppose C1 and C2 are two clauses, right? And if there is a literal L1 in C1 and L1 is complementary literal, suppose L1 is complementary to a literal L2 in C2, then what you do? So in one clause there is a literal L1, and the second clause is having complement of literal L1, which is L2. Then we delete L1 and L2 from C1 and C2 and construct the disjunction of the remaining. Disjunction of the remaining classes. So whatever we get, so that constructed clause is a resolvent of C1 and C2. So what we are doing? So there is a clause C1, there is a literal L1 there, and if L1 is complementary to a literal L2 in another class C2, then we delete L1 and L2 from C1 and C2 and take the disjunction of the rest remaining classes. So whatever we get is known as resolvent of C1 and C2. Okay. Let us take an example here. C1 is P join Q join R, and C2 is negation of P join negation of S join T. So we can see that P and negation of P. So this literal is complementary to each other. right? So since P and negation of P are complementary to each other, the resolvent of C1 and C2 is obtained by deleting these two, and then we taking the disjunction of the remaining classes. So it will be U join R, right? Join negation of S, join T. Okay, so we get this. Okay, so this is known as resolvent of C1 and C2. In fact, now I can give you a theorem here, which is an interesting one. Given clauses C1 and C2 and a resolvent C of, so given classes C1 and C2, so a resolvent C of C1 and C2 is a logical consequence of C1 and C2. So what it is saying, if we have two classes C1 and C2, the resolvent C of C1 and C2 is a logical consequence of C1 and C2. What do you mean by logical consequences? That means, you know, so I will show you that if both are basically if C1 and C2 are true, then the C is also true. That's what we want to say. So let us prove this. It's a very small result. So suppose C1 is L join C1 prime, some other class, and with L is there, you know, C1 contains L. Okay, we are saying, and suppose C2 is negation of L join C2 prime. In general, I have written for some C1 prime and C2 prime. So the resolvent of C1 and C2 is C, which is C1 join C2 prime. By definition of the resolvent, right? I have deleted L and negation of L and taking the join of both. Now I have to show that C is a logical consequence of C1 and C2. I have to show that if C1 and C2 are true, then C is true. Okay, this is I have to show. So in fact, there will be two cases. Let us assume the first one. So assume C1 and C2 are true. We are assuming that C1 and C2 are true, right? Now there are two possibilities. Either L is true or L is false, right? The first case, suppose L is true. If the literal L is true, this implies that negation of L is false. Okay. And in order that C2 is true, if negation of L is false and C2 is true, then this will imply that C2 prime is true. Okay. Hence, therefore, C is equal to C1 prime join C2 prime is true. Second case, if L is false, we can do in the similar manner. If L is false, okay, then in order that C1 is true, C1 prime is true, right? So in that means the whole result is true. So this implies that similar. I think I can just say that similar case. This implies that C is equal to C1 prime join C2 prime is true in both the cases, and hence C is the logical consequence of C1 and C2. Right? So now we are in a position to describe this resolution principle. What is the resolution principle? Okay. So given a set S of clauses, a resolution or we can say deduction of C from S is a finite sequence C1, C2, Ck of clauses such that each Ci is either, so each Ci actually is nahi hoga, each Ci either is a clause in S or a resolvent of classes. Resolvent of classes preceding C, and last Ck is equal to C. And finally, a detection of empty class. So we denote it by this. Empty clause is called a refutation or a proof of S. Okay. So now I am ready to show you that, I will give you an example now actually. I will show that how to arrive at the empty clause. Example is, show that the following argument is correct. Okay, the argument is, if today is Tuesday, I have a test in mathematics or economics. If my economics professor is sick, I will not have a test. okay, in economics. Today is Tuesday. And my economics professor is sick. Therefore, I have a test in mathematics. In math, right? So we have to show that the following argument is correct. If today is Tuesday, I have a test in mathematics or economics. If my economics professor is sick, I will not have a test in economics. Today is Tuesday and my economics professor is sick, therefore I have a test in math. So again, we need to form the propositions. So first proposition is T, today is Tuesday. Okay. M, I have a test in math. Okay. E, I have a test in economics. S, my economics professor is sick. Okay. So these are the so what are the premises here? So premises are T, M join E. Okay. On the statement, S going to negation of E, T meet S, therefore M. Okay. So these are the premises. So normally if you have an argument where P1, P2, PR are the premises and C is a conclusion, to get a proof using the resolution principle, put P1, P1, P2, PR in class form and add it to negation of C in a class form. From this sequence, if empty class can be derived, the argument is valid. So this is a normal procedure through which we are going to deal with it. So let us start. We start putting into the class form. So first clause is C1, negation of T, join M, join E, the first clause. C2, negation of S, join negation of E. C3, T, C4, S, and C5, negation of M. Negation of the conclusion. Okay, that's what I said to you. Negation of conclusion. Okay, so you start putting into the clause form, and then what we do, add it to the negation of C in conclusion form. So that we have added the conclusion form, we have added negation. Now from this sequence, if empty class can be derived, the argument is valid. So let us see if we can derive the empty class. So we need to check if we can get empty from C1, C2, C1, C2, C3, C4, C5, and okay. So from C1 and C2 and C6, we'll have negation of T, join M, join negation of S. From C6 and C3 and C7, we have M, join negation of S. Then from C7, C4, C8, we get M. And from C8 and C5, we get empty class. Therefore, the argument is correct. Okay. So this is all about.
Sir, can you
Yes.
explain how did you write the clauses?
1 minute. Yes. I think my laptop is still about to die. Oh, there is some problem. Yeah. So from here, we wrote the classes like this. Negation of T, right? One minute. Let me put my charger actually. Yeah.
Shouldn't there C3 be T and S?
No, C3 will be T only. C1 is negation of T, join M, join E. C2 is negation of S, join negation of E. C3 is T, C4 is S, and C5 is negation of M. Okay. So actually my laptop is about to die, so probably I will not be able to continue. Anyway, so I think, let us discuss. Okay, so we will stop at this moment, and I think if you have any questions, we can discuss it on WhatsApp and so on. Okay.